Okay, so let's go to our first chapter. So as I said, the first chapter is about um, atmosphere and wind in general. Okay, and we are going to see how we can get meaningful information from the wind data that we observe in the atmosphere. Okay, what type of wind actually what we see in the atmosphere, and how we can actually analyze those data. Okay, so first let's look into atmosphere first, then we go to the second one. So atmosphere, like Earth has a unique atmosphere which supports the life. Okay, and basically it contains gas. Okay, so and there are various gases which constitute the atmosphere, but there are two major components. Like already these things you have studied. So this is just a quick recap. Okay, to complete the course content. So there are two major constituent of atmosphere here, like nitrogen and the oxygen. Okay, and what you see here, the atmosphere, you can divide them into different layers. Okay, the Earth atmosphere, it can be divided into different layers, and generally those are called like troposphere, stratosphere, mesosphere, then ionosphere, thermosphere, and exosphere. Okay, so here you see that I have drawn the temperature versus the altitude and the pressure on this axis. Okay, so for different layers of the atmosphere, these are drawn here. All right, so the very first layer is troposphere, as you can see, which is the bottommost layer, which is near to the Earth's surface. Okay, which is near to the ground. So this is the closest to the ground, as you can see, and in this region you see that as you increase, as you go high, the temperature reduces. Okay, so the rate of reduction of the temperature is around 6.5 degree Kelvin per kilometer. Okay, so this is the rate of reduction of the temperature. So temperature reduces as you go high, as well as here you can see that the pressure observed is around 1000 millibar, or 1 atmospheric pressure, which is 1 bar around. So here in the you can see that the scale is in millibar. All right, so atmospheric pressure is observed here. As you go higher, as I said, the temperature reduces, and the reduction in the rate of temperature, it happens at a certain rate, as well as the pressure also reduces. Okay, but the rate of reduction of the pressure is different. Okay, it is in this particular region, the rate of reduction of the pressure is kind of non-linear. It is not linearly reducing, right? So another thing is the troposphere where, okay, and in this region you find that the air is mostly dense. Okay, and why it is so? Because you can see that the whole amount of weight, or the atmospheric weight, is happening on this particular uh, gas medium here. Okay, so the total weight is acting on this region. So the air in general, or the air molecule in general, are quite densely packed in the atmosphere, in the troposphere. All right, and the range up to what height or altitude it is there, it is actually generally from 9 kilometer at the pole, and can go up to 16 kilometers. So this is not so high. You can see that is up to only up to 10 kilometer. And another thing is, there is no sharp distinction between these regions. Okay, so we can just say that qualitatively it ranges in this range. Okay, 9 kilometers at the pole, and up to 16 kilometer in the equator. Okay, then again it can be affected with the seasonal condition, with the terrain condition. Okay, so that is why there is no clear distinction up to what range troposphere is there. Okay, so generally it is up to 10 kilometers, we say. Then we go to the next layer, which is called stratosphere. And stratosphere, it is like from the tropopause. Tropopause is the topmost layer of the troposphere. Okay, so from the tropopause, it can go up to 50 kilometer. Okay, that will be called as the stratosphere. Okay, and again the top layer of the stratosphere will be called as stratopause. So in this range, you can see that up to 25 kilometer or so, there will be almost a constant temperature. Okay, so this variation in the temperature is not so significant. So we sometimes assume that up to 25 kilometer, the temperature remains the same. And near this top layer of the stratosphere, generally what we see is ozone layer. Okay, that you have already know about the advantage of ozone layer. And most of the high speed jet planes, okay, so they fly in this stratosphere range. And in the troposphere you see that there is a weather condition, like there is season, but in the stratosphere you don't see such thing. Okay, there is no seasonal variation in the stratosphere, only the seasonal variation happens in the troposphere. Okay, and then we go to the next layer. The next layer is it starts from stratopause and can go up to 90 kilometer. Okay, and in this you can see that the temperature mostly reduces. Okay, whereas in the stratosphere you saw that the temperature either stays more or less constant up to certain height or altitude, then it decreases, or sorry, increases. You can see that the temperature range is negative to positive here. Okay, so it increases here, whereas in this case it is reducing in mesosphere. And this is also sometimes called as the coldest atmospheric layer, because you can experience around minus 90 degrees Celsius at certain height. Okay, so this is the coldest layer, sometimes it is called. And in terms of pressure, you can see that the pressure is also gradually reducing. Okay, so pressure is also reducing as you go high in the altitude. So the pressure is not yet that low, so here air still shows its constituents are still there. It is not yet ionic form or molecular form. So you can see that the air still retain its composition. Okay, so that means nitrogen and oxygen is still available in this region. All right. Then if you go to the next layer, which is your ionosphere or thermosphere, which is from this mesosphere to it can go up to about 1,000 kilometers. Okay, and this range basically the temperature increases, and the temperature can be very high. Okay, so the rate of increase of the temperature, you can see that it is at 0 degrees Celsius. If you see here, 0 is here, around 110 kilometers from the ground level or sea level, the temperature is about 0 degrees Celsius. And if you go further high, the temperature can go up to 1,000 degrees Celsius at 150 kilometer, and can go up to 1780 degrees Celsius, which is the peak temperature observed at around 700 kilometers. Okay. There are different cosmic phenomenon also observed in this particular layer, aurora borealis, for example. So yeah, so this is that's why it is called thermosphere, because the temperature range is quite high here, and different ionic activities or cosmic activities also happen. So otherwise it is called ionosphere also. Okay, and the pressure wise, you can see that the pressure is already very low. So beyond this thermosphere, you start to observe exosphere, which is the outer fringe of the Earth, the outermost layer of the Earth, and gradually it merges to the interplanetary space or the vacuum. Right. So in this exosphere, you will just see very few molecules of the air. Okay, so this is what overall the atmospheric structure. This already you have studied in your some of the undergraduate course. For example, flight mechanics, I think, or in your pre-undergraduate, like in your school days, also you might have studied in details. Okay, so this is just a recap for most of you, and you can see that the temperature variation is quite different in the different layers. Some layers it increases, some layers it decreases, and also also the pressure variation is not the same. Like you know that the pressure is gradually reducing as you go high, but the rate of reduction is not the same. Okay. Any question?
So,
Yes.
so in the ionosphere, you have free ions and free electrons, probably at,
Yes.
you said, 1000 degrees Celsius. How is this different from plasma?
How is that different from plasma?
Yeah, because plasma is also like very hot, and it
Hmm.
also contains free ions and free electrons. There's no distinguishable atoms.
Um, okay, so there is uh, not clear distinction in terms of what I will say. In plasma, some form of material properties are also there. Like if you see here, the constituents are mostly um, the molecules of oxygen or nitrogen or gaseous particles. All right. But in some cases, if you talk about mm, uh, plasma in general, we may have other constituents. Okay, so that is one thing. Um, Otherwise, the details. I need to look into that. Okay, so at this point, I may not be able to answer you the clear distinction between the ionosphere, the ionic particles there, and what you observe in the plasma. Of course, both are occurring at the same or similar range of temperature, but material property wise, they varies. Okay, so that is one thing. Other characteristics, I need to look into it.
Okay.
Okay.
Sir, actually, it may be density. The density of the plasma is very high. Atmospheric density may be electrons and ionic density is low. That may be the
Yes, that is what I said. The material properties by property wise, it will be different. Um, yes. Any other thing? I cannot hear. Okay, so if there is no question, let's go to the next one. So there are different scales of atmospheric circulation that we observe. Like you see that this is kind of equivalent to your turbulent scales. Okay, so you get velocity fluctuations and or spatial and temporal fluctuation in different scales, right, in the turbulence. So similarly, when we talk about atmospheric motion, we generally tends to say atmospheric motion are quite turbulent. Okay, because one of the thing is there are different scales of atmospheric circulation. So those can, I think someone's mic is on. Can you please mute your mic? So one of the okay, so the atmospheric circulation in broad scale, you can divide into three groups like micro scale, mesoscale, and macro scale. All right. So in micro scale, which are so here I have shown in terms of the dimensions, like these are in meter. The circulation range or the radius of fluctuation in a way you can say, uh, and the duration of the motion is mentioned here. Okay. So micro scale, generally you observe cloud or the turbulence which are appearing from the building hills or hills. So generally, like if you have different terrain condition, if there is incoming wind, so that may leads to some form of generation of the vortices or the circulation. Okay. Or otherwise the cloud formation or the pollutant coming out of the chimney. Okay, so those have very small velocity scale and the spatial scale also. Okay, so those can be categorized in a micro scale circulation, atmospheric circulation. Okay, so generally the size range is, it can go up to few meters. Okay, maybe tens of meter, you can say that around 100 meter is the maximum, but you can observe here. And the typical duration of this phenomenon, they last for up to microseconds to milliseconds. Okay, so that or maybe few seconds you can say. So that is what the characteristics of micro scale atmospheric circulation. Then if you go for higher length scale or velocity scale fluctuations, as well as the duration or the duration for which this circulation lasts is higher. So in that case, you can consider them as mesoscale. Okay, so for example, thunderstorm, tornadoes, sea breach. Okay, so all these comes under the mesoscale. You can see that the length scale in this can vary up to few kilometers. Okay, here I have defined in particular, like it can vary from 1 or 2 kilometers to up to 1,000 kilometers. Okay, and the phenomenon can last up to few minutes to few hours. Okay, so generally thunderstorm, tornadoes, they are in this particular range. Okay, mesoscale range. Then the last one, which is macro scale, which are quite big, in terms of length and velocity fluctuations. So those comes under okay, so those comes under the macro scale here, and they again can be categorized into synoptic and global scale. Okay, in the synoptic scale, you can see that the range of the circulation can last from 1,000 to 5,000 kilometers, and it can be seen for few days itself. Okay, so generally like cyclones and anticyclones, those are in this particular range. And synoptic scales, you can see that, for example, it can be over a continent. Okay, so it can the whole phenomenon can last over a continent, because the length scale, you can see that it can spread from 1,000 to 5,000 kilometers. So it's quite big. Okay, so it's synoptic scale. Then bigger than that will be called as the global scale, which are long wave phenomenon. Like if something is if the wind is flowing from pole to the equator. Okay, for example, it is covering a very long distance, like traveling from 5,000 or to 2,500 here I have mentioned. So generally it is from 5,000 to higher, can go up to 25,000 kilometers or so. So if the atmospheric circulation, which is quite large in terms of the length scale and as well as the velocity and the time scale, then it will be called as global scale or global scale, and which comes under the macro scale atmospheric circulation. Okay, so in this what you see generally is long waves, easterly winds. Yes,
Sir, can you like please explain like the turbulence in clouds? Like I could not understand that why it's in like micro scale.
okay, so here when I said the turbulence, basically this is not only related to the cloud, it has other examples, like I have said, building hills. When there is a flow around this region, you start to see small scale fluctuations. Okay, so these in general are called turbulence because we can characterize them experimentally, and some cases using CFD techniques, and you get very good approximated data. Whereas if you go for the larger scale, right, the turbulence cannot be defined in so good. Okay, it cannot be defined that accurately. So that is why this small scale phenomenon, where if someone is investigating atmospheric turbulence in general, they look into this range. Okay, the higher range, of course, we see turbulence, but when we are going to do the analysis in this range, they are not so accurate. You don't have the exact experimental information. You just try to do mathematical modeling to see this evolution of the flow regimes. Okay, in these like thunderstorm, cyclone. Of course, you have turbulence there, but you cannot characterize them. Okay, so that's why I did not include turbulence in this range, but generally they are quite turbulent, the flow itself. But when we talk about atmospheric turbulence, it is generally investigated in the micro scale. That is why it is shown here. All right, is it clear?
Like sir, I couldn't understand in terms of the time scale actually. that like clouds
The
like they
formation. Okay, so here when I say the time scale, it is the total time scale, that the evolution to dissipation, the formation of the cloud, and the dissipation itself. It may happen within hour and so. Okay, uh, like we're not talking about the thunderstorm tornadoes. These are small scale clouds. Okay, which can be like when you have pollutants coming out from the chimney, or if you have the summer days, you may get hot spot in particular region, right, around the building areas or around a riverside. So those type of small scale phenomena which can be considered as a micro scale. Okay. Okay. Then okay, so this is the atmospheric circulation that we categorize what that
Sir,
we see
what?
in the atmosphere. Any more question?
Yes, sir. Sir, what is the distinction between a tornado and a cyclone? I mean, why are they in different scales? They are somewhat
We
of similar
we
nature,
will
right?
yes, we will come to that. There are differences based on the velocity values. Overall, it looks. I mean, they overlap at certain range, but when you go for I mean, there will be differences in the velocity scales. Okay, so that detail is there. We will see that. Okay, any more question? Okay, so let's. I cannot hear if someone is speaking. Your mic is not working probably. Can you? Any more question? Someone is speaking. Please mute your mic. Okay. See. All right. So now the question is, how does this atmospheric circulation actually appears at the first place? So for this, one of the very simplest model that Professor Humphrey has developed around 1930s or 40s. So we will, that simplified model is still valid, and you might have studied already in your undergraduate or pre-undergraduate course. So what, how it is explained? Like you consider two tanks, okay, which are filled with the same fluid, and there are two valves. Okay, now at the beginning you have the same temperature condition for both A and B. Okay, tank A and tank B, which are connected by two limbs here, and they are also there are two valves, valve 1 and valve 2. So what I said, at the beginning you have same amount of fluid on both tank A and tank B, and they are on the same temperature condition. Now what you do, you rise the temperature of A, okay, and the valves are closed. So if you rise the temperature of the A, you can see that the fluid here will expand, but the weight of the fluid remains the same. So if you open up this valve 2, there won't be any flow, because the pressure here and the pressure here, due to the weight, hydrodynamic weight, or that will be same at both the place. So there won't be any flow between these two tanks. Okay, now if you open this valve 1, okay, if you open the valve 1, since I have said the temperature at tank A has increased, so basically the fluid has expanded by some amount. Like initially if the label was A, now it has expanded to B. Okay, so because of that, this particular extra height, you can see that, which is not seen in B, tank B. So the fluid will starts to flow in this direction. Okay, so now if both the valves are open, it will starts to circulate between the tank A and tank B. So this circulation can be generated by simply having a temperature difference. That is what you can see here, and generally this is called as a natural circulation, because you are not providing any external source to create the circulation here. Just by having a temperature difference, that of course for that you need to have some mechanism which will generate the temperature difference, and by that itself you can create a circulation. Okay, so That is why it is sometimes called as natural circulation. And
Sir,
now if you
can you please
yes,
explain once more? I couldn't get it clearly.
okay, so let's see, like if you have two tank A and B, as you can see here. Okay, now at the beginning what I said, they are connected by two limbs. Okay, and there are two valves which are closed, okay, at the beginning, and they have same fluid. Okay, both tank A and B has same fluid and equal mass or equal weight. The temperature is also same. All right, now what you do, you raise the temperature of fluid in tank A. If you increase the temperature of the fluid in tank A, what will happen? The fluid will expand, but its weight will remain the same. All right, because the volume remains the same, it is just going to expand. Its weight will remains the same. So
Pressure will increase.
pressure will yes. So if I see at the pressure at C and compare the pressure at B, since the valves are closed, the weight remains the same. So the pressure at C will be same. So if I now open the this particular valve which is connected in limb 2, so will there be any flow? What do you think, Asajit? Will there be any flow if I just open the valve 2?
As pressure is more, uh, if you are just opening two, then simply the pressure will be less at point 2.
No, you see that at that instant, at that particular instant, when I open this valve, the weight of the liquid column on tank A and the weight of the liquid column in tank B, even if it is expanded, the weights are same, right? So whatever pressure I get here, the same pressure I will get here. Okay. So because of that, there won't be any flow. Whereas if you open up this particular valve 1, you can see that because of this extra height what it has achieved here, which is not present here. Okay, because of that you get an extra head here, pressure head, and that is going to create a circulation. Okay,
Okay, I didn't saw that.
so that is what it's a very simplified experimental model which can explain the atmospheric circulation, and this has been proposed by Professor Humphrey in 1940s. Okay, of course there are various limitations to this experimental setup, but it is quite simplified. And with this particular explanation, like if I said there is a higher temperature in the equator and the lower temperature at the pole. Okay, so let's say if I replace tank A with the equator and the tank B with the pole, what will happen? Since there is a gradient in the temperature, the air will starts to move. Like once the air get heated up, it goes higher. Okay, because the density reduces, and it goes to the pole region where the temperature is less. Okay, then gradually it returns back to the equator. Okay, and it completes one cycle. Okay, so this is what the natural cycle, and generally the hot air which drifts towards east, it starts from west and drifts towards the east, these are called westerly winds. Okay, so and the wind which comes from the pole towards the east, towards its west side or towards the equator, will be called as easterly winds. Okay, all right, so these are westerly winds which are warmer and easterly winds which are colder generally. But this is very simplified model, and we don't see such simplified circulation in the atmosphere. Okay, so what causes why this simplified model doesn't work? Because of various reason. One of the reason is in general the temperature distribution in the atmosphere, they are affected by various things that you already aware of, like there are solar and terrestrial radiation, for example. Like you know that the earth axis which is inclined at an angle to its orbital plane, right? It is actually inclined by 66.5 degree to its orbital plane of the sun. Okay, so if it is inclined, the equator region gets maximum amount of sun throughout the year. Okay, throughout the year, the equator region gets the maximum amount of sun, whereas the polar region doesn't get the same amount of the sun. So you can see that there is a temperature difference which appears because of the Earth rotational axis itself. Okay, placement of the rotational axis in certain way, and because of that there is temperature gradient, and which can be considered as solar and terrestrial radiation. Okay, so the amount of solar energy that particular region of the Earth receives, that varies. Okay. Then there is also radiation in the atmosphere. Like you have seen that as we move higher, the atmospheric layers are changing, right? So in different layers of the atmosphere, you have different density of air. Okay, that corresponds to the particular pressure value that region contains. So since the constituents or the composition of the air varies as you move higher, or to move to the different atmospheric layer, so the amount of radiation also changes. Okay, so the radiation in the atmosphere also changes, and that also affects the temperature distribution. Then again, the third factor is compression or expansion of the air. So as we have already discussed, the air near to the ground surface are quite compressed and dense, but as you move higher, it gets less and lesser dense. So the compression and expansion of the air itself, it also affects the temperature condition. There are other things like molecular AD conduction. So in certain terrain like urban region, you might get more amount of this circulation, atmospheric circulation, whereas if you go to the flat land, there might be a different scenario itself. So this turbulent ADs tries to dissipate the thermal effects. Okay, so because of that, again, the temperature distribution is affected in the atmosphere in general. Then evaporation and the condensation of the water vapor. This is already, you know, that the water cycle, like in some region of the earth, you have a higher amount of evaporation, like in the sea or the ocean region, and in the dry land you don't have that particular water cycle. Okay, so these are the factors which affects the temperature distribution in general throughout the Earth's surface, and because of that, this simplified one cellular atmospheric circulation model doesn't hold good. Okay, so we said that air in general gets heated up in the equator and goes to the pole and comes back. But this is not so simple, because the temperature distribution in the other region varies. Okay, and there are various factors that we have discussed. So these tries to modify that simple cellular one cellular model, and the more appropriate one which are generally followed, and there are, again, this is the intermediate one, I will say, the tricellular model, which is considered to be okay, kind of okay model to represent atmospheric circulation. There are better cellular models which we are not going to, of course, discuss here in more detail. So the tricellular model, which is better approximation than the single cellular model. Why it is so? Because it includes all those factors that we have discussed, and what it does, it breaks that one cellular model into 3 cells. Okay, so there is one cell which is very nearer to the equator and goes from 0 to 30, or which is horse latitude. So one particular cell, thermal cell happens here, or atmospheric cell happens here. Then the other one, which is from 30 latitude to 90 or 60 degree latitude. Then there is another one which is from 60 degree to 90 degree or towards the pole. So these 3 cells are named differently. One is called Hadley cell, the other one is called Farrell, and the third one is called polar cell. Okay, so Hadley cell is the one which is the nearer to the equator. Okay, and in this case, you see the air condition is mostly wet condition, like it contains a lot of water vapor, and like the thing, the phenomena is quite self-explanatory here. Since you know that temperature in the equator is quite large, so due to that, the air gets heated up here, and it also captures or absorbs a lot of water vapor along with it, and it tries to goes up. Okay, so when it is going up, it can either go towards the north directly or towards the pole on this side directly, or it can actually what happens after a certain distance, it experiences a different what do you call different temperature distribution. All right, because of the these factors what we have already discussed. Okay, so these factors which affects that up, I mean, so moving up air which is getting colder, like when the air is moving up, it is getting colder. So what it does, it tries to fall down. So some of the air falls down and form a circulation here, and some of the air it continues to move up. Okay, and at the same time, the polar cell formation, it happens because at the pole, what you get the lowest amount of sunlight, and because of that, the air is quite dense and the pressure in that region is quite large. All right, so since the pressure in this region is large, the air will try to move down. Okay, so when the air is moving down, some of the air which are coming from this particular headless cell, they also interact here and they form a polar cell in this region. So this cell, headless cell, then the polar cell, intermittently there is another cell is formed which is ferrule cell. Okay, I think this you might have studied in your geography already. So I'm not going to explain it in more detail, and if you want to refer back, just go and refer back. So another thing to note down here is in this headless cell, you start to see a lot of trading happen in this region. Okay, because the wind in general in this case is quite steady. Okay, it is not a very windy situation since the air itself contains a lot of water vapor, so it cannot move very fast. Okay, whereas in so a lot of trades happen in this, and you start to see a lot of rainforest also. Okay, so near the equator region, you also know that there are a lot of rainfall, so the rainforests are also visible. Whereas this horse latitude and above, this ferrule cell, you only see the sinking air where there are less rainfall and lot of deserts. Okay, so in this region, both in the North Pole and South Pole, you start to see a lot of desert region in this ferrule cell, where you don't have basically the water vapor content or the moisture in the air is lesser, and it can move very fast. Okay, so that's why the deserts are there, and generally those camels or the horse, they are used to transport the cargoes, okay, or goods. So that's why otherwise the name is called as horse latitude. Right? And in polar cell again, like because of the dense air, low sunlight, and the compressed high pressure due to the compression, so you get a higher or the dense air situation in this case, and that forms another cell, polar cell here. Okay, so this in general is a quite good approximation for the atmospheric circulation, but there are various other models which are recently developed and which approximate in a better way. But many a case, many meteorological subjects, they also follow this particular model. We will not discuss any further on this. All right. Okay, so I think that's all for today. I will start tomorrow. I mean, I will continue tomorrow on this. Any question? So far, what we have discussed, already you have studied probably in your school days. So nothing new. Just go and recap. If you don't understand, then I can help you in understanding further. Okay, but these are already what you have studied. All right. Okay, Okay, then if no question, then we stop here today. Let me take the attendance first, download this. Okay, another thing, do we have any vacancy to shift the class from Friday to Monday? Like what I was thinking, since we have 3 consecutive days, Wednesday, Thursday, and Friday, I feel like it will be better if we have 1 day gap in between. So either we can shift Thursday's class to some other day so that it will be more, comfortable to have the lectures, not in a consecutive manner. Maybe you can get time to read and can have the doubt and clarify that.
So what will be the preferable time for that?
Any time. Like I have no lectures as such. I mean, I will have another lecture starting from in March, so I'm available most of the time. So if it is in the evening slot, that will be better.
I think we can
Sir, I do not.
Friday slot. It's 8 a.m. in the morning. I don't think everyone will be joining at that time.
Friday slot, right? Yes.
Yeah.
So that is what I wanted to. I mean, if we can shift it to a more comfortable timing. So one thing is having a day break between the 2 lectures. The second thing is Friday is quite early. It's difficult. I know that. So so we need to have 2 timings in that way. Okay.
If we can have sometime somewhere in like Monday just before
Yes.
lunch, maybe.
Is everyone available? Then
I have
we
a
can
class
have it.
from 12 to 1.
12.
So maybe on Monday from 11 to 12,
12.
or
Yeah.
10 to 11.
No,
Yeah,
10 to
yeah.
11 I have a class.
I have class.
No, sir, I have a
not
class from 9 to 11.
Monday 10 to 1.
So 11 to 12.
Sir, I have class from 4 to 6, so evening slot is also not available.
So every day 4 to
Preferably
6.
within the morning.
Monday 3 to 4
Sir,
will be.
why don't we put a Excel sheet and say the
Yes,
timings
I
that we
think
have, because in this way
that
there is
yes, that will be not
yeah.
so convenient to discuss. So let me share the Excel sheet, or otherwise you can discuss that in the chat box itself, like either in the evening slot in any of the day, okay, or in the morning slot when all of you are available. We can shift the class. It can be in the late evening also, like beyond the class hours is also fine, like from 6 to 7 also we can have in the evening. That is also okay with me. Okay.
Sir,
So
instead of, I think instead of discussing what the class time should be, instead if we just let's say propose a particular window of time and ask for free slots of everyone there, it will be just simpler for everyone to decide.
Okay, all right. Yeah, that sounds good. That sounds good. What about Monday 6 to 7?
Yes, sir.
That
I
will
have
be
a
fine, sir.
class during the evening hours almost every day, till either till 7 or 8.
Achha.
Sir, nobody said anything about 11 to 12 Monday.
That will be fine, sir. Monday to.
No, I have it 11
No,
in
I
the
have
evening.
class from 9 to 11. And 11 to 12 as well.
11 to 12, does anyone have?
I have class at from 11 to 12.
I have class from 9 to 12.
Okay, okay. I think let's do this
So
discussion
we
over
can
the
have it
Excel sheet.
on Monday from 2 to 3.
2 to 3. Monday 2 to 3 sounds good.
Yes, sir.
I have class.
Yes, sir.
Yes.
Now someone has class. Someone has class. Just
And 3 to 4.
3 to 4, Monday 3 to 4.
3 to 4.
Yes, sir.
Yes, sir.
So I have a class 3 to 4.
Oh,
Okay.
3 to
4
6
to
I
5.
have.
Oh,
3 to 6
Okay.
actually.
So,
So I will
honestly, I think
prepare
8 to 9 is fine.
8 to 9 is fine. I'll prepare an Excel sheet. There I'll mention some of the time slot. If someone has some issue in that time slot, please let me know. Then we can see. Anyways, tomorrow we are going to meet again. So then we can discuss, okay, about this. All right. So till then, take care. Bye bye. It's already 12, I think. Okay. So we end here today.
Thank you, sir.
Thank you,
thank you,
sir.
sir. Thank you.
Thank you, sir.
Thank you.